So, good evening. Welcome to this second night of the Quantum Technology School and this presentation, which looks at what I think are the key skills for being a physicist or being a physics student. You're all doing physics at the moment. You're maybe thinking about doing physics or indeed computing science, of course. And a lot of what I'm saying here equally applies to any scientific discipline, but we all know physics is the only true science. So we'll call it thinking like a physicist. And what I want to talk about is the underlying thought processes, really, that are there no matter what you want to do. So, and key to it is wondering. You wonder about things. So let's give you some examples. Lord Kelvin, physicist with a long history with the University of Glasgow itself. He wondered about many things in his career. For an example, he wondered if it would be possible to send electromagnetic signals across the Atlantic Ocean. Dame Jocelyn Bell Burnell wondered about strange repeating signals she was detecting in her experiments and wondered what that could mean. Isaac Newton wondered why apples kept falling on his head. Wonder was where all of their work started. And whenever you do anything scientific, it does start with this idea about wondering what's going on. If you're going to do a detailed scientific project, if you want to win a Nobel Prize, if you want to win millions in research money, then you need to do a lot of work, you need a lot of time, you need that money. But before you can do all that, you really need to have some idea of where you're going. And you can start yourself going by wondering roughly what values something you want to measure could be. And you make estimations, or you could make an approximation. And as you can see on the slide, really what we're doing here is guessing, but we're doing informed guesswork. That's the key to being a physicist. Now, let's have a little think about this. If you had a chance to look at the academic pack, the activity pack we sent out, there were a series of multiple choice questions where we asked you to estimate several things. Now, whether you've tried them or not, I don't know, but we also tried a few of these on our Twitter over the last week, and we got some interesting responses. So this was one of the questions we tried. What's the volume of a typical physics classroom? Now, the idea here is that none of us know exactly what it is, but you could probably work out roughly what it is with a simple calculation. So what I believe a typical classroom is about 150 cubic meters. So if you were taking part on Twitter and you gave that answer, you agree with me. I don't know it's right, but of the options that were there, it was the most sensible based on what I do know. So I don't know what the volume of a room is, but I do know that people are usually below 2 meters tall and there's plenty headroom. So it would be reasonable to assume that a room was about 3 meters high. And then if you were to look around a room, then usually it's square or rectangular, and the width isn't orders of magnitude greater than the height. And orders of magnitude, as you probably know, it means powers of 10. So it felt right to decide that the volume of a room was about 150 cubic meters. Now, the reality is there probably aren't that many classrooms that are that size, but I would lay odds that they're all hundreds of cubic meters. That's the important bit there. And that's the key to making estimations, is that you get a rough idea of whether or not you're looking for something that's huge or small. And the more you do it, the more comfortable you become making these types of estimations, which was why the questions in the activity pack asked you to be honest about how confident you were about your estimate. Were you blindly guessing, or were you basing it on a calculation you did? Here's another example. How tall is King Kong? So again, I gave some options, and it was as much about trying to work out which you think were the right answers and which weren't the right answers. The key to this one was the fact you're given a picture, and the cliche is a picture paints 1,000 words. There's always information in the picture that can give you some information that might give you an idea of what the answer might be. And that's one of the things you want to develop as a physicist, is when you're looking at a set of equipment or an example in a textbook or an exam book, there's some information there, usually more than you might realize, that will help you answer the question. So in the case of our King Kong here, looking at this picture, and I have to say, I don't know what the answer is. I'm sure Google will tell me, but I didn't want to find out what Google thought. But I did know that in that picture, I can see that they're fighting on a rather unfortunate aircraft carrier, and there appears to be 5 decks behind. So if that's 5 decks, that gave me a little scaling bar, and there were 5 of those for the full height of King Kong, give or take. And so 25 decks. How high is a deck? Well, like we estimated our height of a classroom, about 3 meters. So I think he's about 75 meters. I don't know if that's true, but I can make a series of assumptions which I can defend to arrive at a logically generated guess. And that's basically where all research starts, with a logically argued guess. And then you flesh that out to try and win the grants and the Nobel Prizes. So our King Kong example makes use of scaling, and scaling can be really helpful if you want to try and make estimation calculations. So for instance, let's fall on the perfect building brick, your standard 2x4 Lego brick. If I wanted to count that Lego brick, that's easy. It's 1. There is no issue there. If I wanted to count those 2, again, I think we can manage that. There are 2. Pushing it a bit here now, we're into 4, but we can still count it reasonably. Then we get more and more, and it gets to a certain point where counting is no longer the most efficient way of getting an answer. Scaling might be a better way of doing it. Now, obviously, if what you're trying to do is come up with an exact answer, then you need exact measurements, you need exact counting. But nearly always, what you need is just an idea. So let's take our block of lots of Lego bricks, and you could measure it. So I measured these blocks, 9.5 centimeters by 9.5 by 4.7. So you can measure the volume of the block. You can measure the volume of one brick, divide one by the other, 87.5 bricks by estimation. Now, because this was a manageable chunk, I did count them, and it was 90. So there we've got order of magnitude agreement between the estimation and the actual count. So this is an example of, again, the way physicists approach problems is that you want, it's that order of magnitude. That's the critical bit. Now, for a block of Lego bricks, the saving in effort is minimal. It probably takes about as long to do the calculation as it would to count the bricks. But the idea is that scaling becomes more and more valuable the fiddlier the calculation you're trying to do, for instance. So let's take an example. Suppose you had a jar of marbles and you wanted to know how many marbles were in there. Could you count it? Probably. It probably wouldn't take that long. Could you do it by some sort of scaling factor? Yes. Would it be much quicker? Probably not. You might recognize the jar. There was one of those in the activity packs with the exercise to find out, estimate how many beads were inside there. Can you count it? It is doable. I have done it. We'll come back to that later on. But it was certainly a lot quicker to do a scaling calculation. And then, for instance, a jar of rice, could you count it? No, that's not going to happen. But you could do a scaling calculation. So the power in scaling is that basically the length of time it takes to make a scaling calculation, that's kind of constant. The amount of time it would take to, in this case, count things gets longer and longer and longer. So scaling, making estimations is a very efficient way of giving you an idea of the answer. So let's take the marbles as an example of how you could do it. So 2 ways that I think you could do it. You could do it by volume or you could do it by mass. So if we do it by volume, then we've got a cylindrical jar. And if we assume the diameter of the jar is D and the height is H, then I'm sure you already all knew the volume of a jar. And I'll spare you the calculations. You get 7.25 10 to the 5 cubic millimeters. The marbles are spherical, so 4/3 pi r cubed, which gave, when I ran the calculation, 2.31 10 to the 3 cubic meters. Divide one by the other, and we get an estimate of 314 marbles. Now, actually, if you're doing this kind of order of magnitude calculation, this estimation, all we really care about are these powers of 10. So we had a volume of a jar of 10 to the 5. You've got a volume of a marble of 10 to the 3. So it's that ratio we actually really care about. So 10 to the 5 divided by 10 to the 3 is 10 to the 2, or hundreds, which is what we got. Now, if you do it by mass, so a full jar was 891 grams, an empty jar is 44 grams. I measured, so I knew what the difference was, so I could work out the total mass of all the marbles. I weighed 10 of them, which allowed me to work out an average, which allowed me to work out that there would be 151 marbles based on mass. Now, there's a factor of 2 difference there, but for this kind of estimation, we don't care factors of 2, because they're both hundreds. That's the idea. These estimations, the goal is to agree orders of magnitude. If we can agree numbers, great, but it's the order of magnitude that matters. Now, actually, if you count the jar, there's 153. So in this particular case, doing it by mass was the more accurate way of doing it. But whether you counted them or estimated by mass or estimated by volume, you got the same order of magnitude. Considering the jar had a label on the other side from the photograph that said 150, we came out on top to the tune of 3 marbles. Now, you had the beads. Now, I don't know if you had a chance to do the calculations, but you can do the same thing. You could estimate by volume. In this case, the beads are cylindrical and so is the jar. And that gave an estimate of 210 to the 3, or thousands of beads. If we do it by mass, then we had 850. So we're hundreds, although we're not far off the thousands. So we're not quite getting order of magnitude agreement. We're just shy of the thousands in one, and we're past it in the other. And I did say earlier, it is doable. You can count them. And I did. And in that particular jar, there are 789. Now, I don't know how many there are in the jar your school received. I didn't count them all. We sent out 33 of them. But there was very good agreement there between the mass and the count. And it took me a lot longer to count them than it did to measure it. So that was a good example of where the estimation can be really helpful. Actually doing those jars allowed me my own example of an estimation calculation. I had to work out if I had enough beads or if I needed to make another trip to IKEA. So I carried out my own estimation calculation. I had filled 8 jars when I had emptied the right-hand one a bit. I knew I needed 33 jars, so I was able to work out how much, in theory, I should be able to fill from 2 of them. And after I had filled 33 jars, it said I should be able to fill nearly 34. After 33, I still had some left, which is why you also all got a bag of spare beads. So it was a nice example of making use of an estimation calculation and saving me an unnecessary trip back to IKEA. Although granted, there's no such thing as an unnecessary trip to IKEA. Every trip to IKEA is necessary. Okay, so what am I trying to tell you? I'm trying to tell you that physicists start by wondering about things, but they then need an efficient, simple way to arrive at an idea of what the answer is going to be. Because there is no way you could spend years, and you wouldn't want to, trying to answer a particular question if you had no idea what the answer was. So it makes your life a lot simpler. It allows you to spend your time in a more concentrated manner. So let's do a physics example rather than a beads one. Suppose you wanted to develop an experiment that measured the gravitational force between 2 people. So first of all, you need an equation. Every estimation, sadly, you need to know some form of equation. When we were counting marbles, it was volume equations. In this case, we need to know that the gravitational force is big G times mass times r squared. So we've got the 2 objects, in this case are 2 people. We've got the gravitational constant of the universe, and we've got the separation. So first of all, when you want to tackle this type of question, you ask yourself questions. In this case, what do all the symbols mean? I just answered that. Then you make some assumptions. So we're trying to work out the gravitational attraction between 2 people. So let's assume they have the same mass. In reality, is that likely to be the case? No. but you're aware of the fact that physicists rarely deal in reality. What we want is representative people. And if representative person 1 has a certain mass, then there's no reason why you can't just assume the same for the second person. Then you'd want to assume that they were relatively close together, and we'll assume that the gravitational constant universe is what it always conventionally is. Then you want to estimate values for assumptions. So when it comes to this, what you want to do is you want to try and pick numbers that make your life as simple as possible. So what I tend to do would be taking a mass of 100 kilograms. It's a nice, simple number. It's reasonable. People tend to be tens of kilograms or just into the hundreds. They're not thousands, they're not tens of thousands, they're not grams. So you pick a number that's reasonable and easy to work with. And you pick a sensible separation. Now, I must admit, normally I would say pick 1, because 1 is the easiest number to pick. But of course, we're still living in a COVID environment, so 2 meters is probably a safer bet. So then you take your numbers and you put them in the calculation. Spare the calculation, you arrive at an approximate solution. Now, for the numbers I've picked, we discover the force is 1.67 times 10 to the minus 7 of a Newton. So the force between 2 people due to gravity is very small. Now, hopefully you knew that. You know when you jump in the air, you're drawn back down to the earth. You're not drawn into the arms of the person next to you by gravity. That's not what happens. So you knew it was a small effect, but you could do a very quick calculation to back that up. Now, we could change the numbers a little bit. We could have gone for 1 meter separation instead of 2. We could have gone for 75 kilograms instead of 100. That might make the number a little bit more accurate, but it wouldn't have greatly changed this factor here, this order of magnitude, which again, as I've been saying all through, that's the key bit. So you could very quickly do a calculation that tells you, I need to develop an experiment that measures a very small force, which saves you a lot of time in your experimental design. Right, so that's this key thing, and that's what underlies the thought processes of physicists and they're carrying out experimental work. What is the size? Is it a huge thing? Is it a small thing? And the more physics you do, the more experiments you do, the more questions you do, the more you'll have a feel for what sort of answer you'd expect. As I say, hopefully you were expecting that calculation to produce a small force because you know something about how force works. Similarly, if you were asked to calculate the mass of a particle, in this case a proton, if your calculator told you it was 510 to the 32, I would hope you would look at that number and go, that somehow doesn't seem right. If you were being asked to calculate the mass of a sun, that might be right, but not a proton. So again, looking at that order of magnitude is what a physicist does when they're doing an experiment, when they're planning an experiment, but it's what you can do when you're doing calculations in class, because you can look at that and you can go, does that seem right? Again, it underpins the way that you think about the questions. Now, that's all well and good when you're dealing with things you do know. Like, for instance, you know particles are very small, you know stars are very big, you know the gravitational attraction of people should be very small. But you can extend this to a situation where you're trying to do the calculation or an estimation where you don't have a feel for the answer, which kind of brings us back to our size of King Kong. You look for things you can do. So what we do is we come back to our 5-step process, the exact same 5-step process we walked through a minute ago. We ask questions, we make assumptions, we estimate values, we combine them, we produce an approximate solution. And this type of question was a favorite of a 20th century physicist called Enrico Fermi. And you may have heard of his classic example, which was, can you estimate how many piano tuners are there in, and he would pick a city at random. Now we could do that here. But what we're going to try and do is we're going to try and do a slightly more useful example. We're going to try and work out how many physics teachers there are in Scotland. Now, to do this, I'm going to stop this sharing my spreadsheet here, and I'm going to try and share my tablet so that we can do a little calculation together. This is always a little hit and miss the first time through, as it's reliant on technology talking to technology. And the first time through, it's failed. So we stop there and we go to more old-fashioned technology. And we cross our fingers. And we try again. Excellent, there we go. Good old-fashioned technology. Stick with cables, never move Wi-Fi. Right, what we've got here is a worksheet I prepared earlier to try and answer this question. And I want a little interaction from you guys. In the Zoom chat, I need some information from you. To work out how many physics teachers we have in Scotland, the first thing we need to know is how many people are there in Scotland. I looked that one up because, to be honest, I know it's millions, so I already know the order of magnitude, but I thought for the purpose of this, I would cheat and I would use Google. And I checked on Google, and apparently the population of Scotland is that 5.5 million. Now that, according to Google, is the answer. That must be an estimation. I find it highly likely it's exactly 5.5 million. But it suits our purposes because order of magnitude is what we want. But now we need to work out how many pupils there are in schools. So this is where I need your help. In the chat, could you quickly type how many people are in your close family? As in basically the number of people in your home, including yourself. Is it 3, 4, 5? Just fire away, fire away. Lots of answers are firing away in there. Okay. I think, there's some votes coming in there. I'm doing a very rough calculation as we go here. So skimming back through here, it looks like 4 is the most popular answer. So we were going to go with 4. Right. All right. So the number of families we're dealing with then is 5.5 million divided by 4. Now, thankfully, I got some numbers in front of me already. So that's 1375000. Okay. Right. Now we need to know how many people there are, roughly speaking, in high school in your family. So in your household, how many people are in high school, including yourself? Ones and twos and none. All right, let me skim back through these answers. We are coming out at, okay, I'm going to go with 1. There seems to be it's close to 1 and 2, but to keep things simple, let's go with 1. So that brings, what does that bring me down to? That means we've got, now we can do some calculations, the number of high school pupils. We can estimate that. That's just 1,375,000 times 1. I think we can all probably do that one in our heads. All right, now what do we need to do? So each of these boxes on the screen is representing an assumption I am making, and then we're trying to put a number on those assumptions. So we've assumed, so far we've assumed there's 1 and a bit million pupils in high school in Scotland. Now we need to work out how many of them need a physics teacher. Now this one's not easy to do because now we're moving into definite approximations. However, we can make some sensible assumptions. There are 6 years in secondary school, and roughly speaking, you make your major course decisions at the end of secondary 2, secondary 4, and then when you're finished. So I think it's not unreasonable to take our number and divide it by 3. So if we do that, then that gives us something like 450,000, I think. Let me just double check that. Yes, give or take. So we've got 450,000 in each of our year groups. Now, the reason I've split them is because depending on which of those combinations you're in, there's a variation in how much science you do. Because as you remember yourselves, in S1 and 2, you tended to do physics and chemistry and biology, and then you tended to do only 2 of those in secondary 3 and 4, and then usually 1 or so in the other. So, to try and get a more meaningful number, since in first and second year, you tend to do 3 sciences, it's not unreasonable to take that total number and divide it by 3 to get the number of students we're dealing with for physics in S1 and S2. So we've got 150,000. Now, I'm making an assumption here that only physicists teach physics in secondary 1 and secondary 2. Now, we know that's not true. Some of you have suffered through biologists trying to teach you physics in secondary 1 and secondary 2, or even worse, the chemists. But let's just assume that proper teachers are doing this. Now, for scaling secondary 3, 4, secondary 5, 6, I'm being very arbitrary here. You know yourselves, your classes tend to get smaller as you went up. So I'm assuming that there are less people doing physics in secondary 3 and 4, and then less again in secondary 5 and 6. I've picked at random 4 and 5. Well, not random, sorry, that's not quite true. They're arbitrary choices. But remember, the goal here is to generate an estimation, an order of magnitude. So it doesn't matter exactly. We wouldn't want to divide by 10 or 100, because that would make it meaningless. But it's a reasonable number because it'll keep it in line with what we're looking at before. So if we take our 450,000 divided by 4, that's that, I think. And if we divide it by 5, that one I can definitely do off the top of my head, we get that. So now we've got these 3 groups, combine those. So we add these 3 numbers together to give us our total number of pupils. So by that estimation, we've got let me see if I got 352,500. And as you know, in Scotland, you can only have 20 pupils in a physics class. So divide that by 20, and we should get our the number of physics classes we need. So we've got 352,500 divided by 20. That's about 17,000. I've made a bit of I've rounded down a bit there, but again, order of magnitude is key. It's the number of zeros. Right. Now, how many lessons are in the school day? That's important. Now, I need your help with this again. So at your school, how many periods are there? I know it's a bit vague, so let's go for roughly 50-minute, hour-long periods. Are there 5, 6, 7, 8? Wow. 7, 6, 7, 6, 7. It's looking like 7 coming in, or 6 or 7. That's true. Some school days are longer than others. So let's go with 7, I think. Look like the dominant answer there. All right. So if we've got 7, then what do we have? Then our total number of teachers is the number of classes, which is our 17,000, and our number of lessons in a day. So 17,000 divided by 7 is about 2,400. Okay, so very rough, very quick estimation suggests a few thousand physics teachers in Scotland are needed. So let me stop that and come back to my PowerPoint. So how many physics teachers are there in Scotland? Surprisingly hard to work out, but I did manage to find a website. The internet came to my savior again. And according to that website, which for data for 2018, it's a little out of date now, but it said there were just shy of 1,000. So our very crude estimation that took us a couple of minutes told us there were some thousands. The reality is there are about 1,000. So it's not that wildly off, but we made some very broad sweeping generalizations, but we still got that order of magnitude agreement. And that is the key thing to what I want you to take away from this presentation about thinking like a physicist. We wonder about things. We wonder how big something is, how small it is, what is it, what's causing it. Eventually, you will want to do a detailed calculation or a detailed measurement or conduct a detailed theoretical examination to know exactly what's going on. But before that, you want to estimate things, you want to approximate, you want to have a feel for what the answer is. And you can, the more physics you do, the more experiments you do, the more confident you will feel doing that kind of calculation. And it's not something that comes quickly, it is with practice. At your stage at the moment, I suspect most of you are quite uncomfortable being vague in a physics context. Vague is for art. Vague is for English. Physics is precise. And it is to an extent. But the more physics you do, the more you realize that being comfortable with approximations is key. And it can save you a lot of time and a lot of effort. But it all ultimately comes down to just taking a logical approach to any question you're faced. Break that question down. Think about what it's telling you. To be honest, the same advice you're probably given by your teachers when tackling exam questions. Break it down. Look for clues, look for words, look for numbers. Look for the small piece of information and then use that to build up to an answer. And that's the same process that every physicist has ever used when doing anything, whether it's advanced quantum mechanics, whether it's gravitation, whether it's optics, whatever your discipline of choice that you might be thinking about doing. It starts with these approximations. It starts with having an idea of what you want, and then you build up from there. Whether it's about something you know or you don't know, it's amazing how much information even your day-to-day life can give you to help you answer even the hardest physics questions. I hope you found that useful. And thank you very much for listening. And I'm very happy to take questions. And I'll just stop the recording at this point, as we did yesterday.